When the Voyager 1 probe crossed the invisible boundary of the solar system, its instruments picked up on something strange. Beyond the solar bubble, the space around the spacecraft seemed to grow denser. Specifically, the plasma density, the concentration of charged particles outside the heliosphere, was climbing. 6 years later, its twin, Voyager 2, confirmed the same discovery. Right now, both machines are pushing deeper into the space between the stars. Their journey will last so long that they'll outlive not just their creators, but possibly the very stars in our sky. But there's one detail in this whole story I still can't quite wrap my head around. How are we still receiving anything from them at all? How do spacecraft built half a century ago, now tens of billions of kilometers from Earth, manage to send us data about phenomena like this in real time? The story of these machines starts with a rare cosmic coincidence. In the mid-1960s, a graduate student at NASA's Jet Propulsion Laboratory, working through orbital mechanics, stumbled onto something remarkable. In the late 1970s, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were about to line up in just the right configuration. What made this so special is that planets orbit the Sun at different speeds, so an alignment like this only happens once every 176 years. Before that window, humanity simply lacked the technology to reach that far. After the planets drifted apart again, the opportunity would be gone. This really was a now or never moment. Here's the thing, you can't just fly in a straight line through space the way you'd drive on a road on Earth. Everything is constantly moving in curved orbits, endlessly tugged by gravity. To reach a distant planet, a spacecraft can't simply push forward. It has to keep adjusting its path, and that takes an enormous amount of energy. Humanity didn't have rockets, capable of carrying enough fuel for a direct flight to Neptune. A straight shot would have taken a punishing 30 years. But this rare planetary alignment made a gravity assist possible. The principle works something like a slingshot, except instead of an actual sling, the spacecraft gets caught by the invisible pull of a planet's gravity. As the planet moves along its orbit, its gravity grabs the approaching probe, drags it along, hands off a slice of its own orbital energy, and flings the probe onward with a massive, essentially free boost in speed. This trick cut the travel time from 30 years down to just 12. NASA jumped at the opportunity and hedged its bets by building two identical probes, engineered for maximum fault tolerance, redundant computers, backup thrusters, dual communication systems. Voyager 2 actually launched first, in August 1977, on a longer, slower path designed to visit all 4 planets. Voyager 1 launched 16 days later, but on a faster, more direct trajectory. Its job was to overtake its twin and carry out a detailed study of Jupiter's and Saturn's largest moons. Thanks to its higher speed, Voyager 1 pulled ahead even before reaching Jupiter. What it sent back changed science forever. Researchers had expected to find boring, dead rock. Instead, Jupiter greeted them with violent turbulence. Voyager 1 captured a series of images that were later stitched into a time-lapse back on Earth. And for the first time, scientists saw that Jupiter's atmosphere wasn't some static painting. It was a living machine of jet streams, vortices, and storms. And on the moon, Io, astronomers spotted active volcanoes venting bluish plumes. Next came Saturn, wrapped in its system of hundreds of rings. This is where the twins' paths diverged, and it was entirely by design. Voyager 1's trajectory had been plotted to swing in close to Titan, the only moon known to have a dense atmosphere. Titan's gravity pulled so strongly that it sharply bent the probe's course, flinging it up out of the plane of the planets and off into deep space, sacrificing any chance of visiting the remaining worlds. Voyager 2, meanwhile, continued the grand tour, becoming the only spacecraft ever to visit both ice giants. Approaching Uranus, the probe found a bizarre anomaly. Not only does Uranus spin on its side as it orbits, but its magnetic field is tilted a striking 59 degrees from its rotational axis, and its magnetic center sits offset from the planet's core. For comparison, Earth's magnetic field behaves roughly like a giant bar magnet, and tilted only about 11 degrees relative to its spin axis, with the source of the field sitting deep inside the planet. Uranus is far stranger. Its magnetic axis is skewed nearly 59 degrees and significantly off-center. As a result, as the planet rotates, its magnetic shield doesn't spin smoothly at all. It wobbles wildly through space. The probe then reached Neptune, recording the strongest winds anywhere in the solar system, gusting up to 2,400 kilometers per hour. Picture winds at that speed here on Earth. They'd be supersonic. They wouldn't just tear roofs off buildings. They'd rip through structures, vehicles, and infrastructure like a storm category we don't even have a name for. After Neptune, Voyager 2's cameras were switched off. In 1990, following the now famous pale blue dot photograph, Voyager 1's cameras were powered down as well. There were no more nearby worlds left to photograph, and every watt of power was becoming too precious to spare. From that point forward, why the probes' scientific value shifted to their other instruments. Particle detectors, magnetometers, and plasma sensors, tools that sense invisible radiation and magnetic fields and beam back data no telescope could ever capture. The cameras are dark now, and the spacecraft drift through the cold void between the stars. And yet, the strange thing is that even after nearly half a century, invaluable scientific data from the edge of the solar system is still making its way to Earth. Which brings us back to the central question: how are we even still hearing them? To appreciate the scale of this engineering feat, you have to look at the hardware itself. The combined RAM across all 6 computers on each Voyager totals a mere 68 kilobytes, less memory than the chip inside a modern car key fob. The smartphone in your pocket is millions of times more powerful than the probe's entire flight control system. Data gets collected and stored on a vintage 8-track digital tape recorder, technology that today belongs in a museum. But the truly mind-bending part is the communication system. Each spacecraft beams data back to Earth using a transmitter, putting out roughly 20 watts of power, comparable to the dim bulb inside your refrigerator. The Voyagers now sit more than 24 billion kilometers away, a radio signal traveling at the fastest possible. Speed in the universe takes more than 22 hours just to cross that gulf. Over that unimaginably long journey, the radio wave spreads out across an enormous area, and only a vanishingly tiny fraction of the original signal ever reaches Earth. By the time it arrives, its power has dropped to a fraction of an attowatt, a unit I'd honestly never even heard of before researching this. Less than 1/1000th of 1/1000th of a watt. It's a radio whisper so faint that without giant antennas, it would simply vanish into the background noise of the universe. So, how do you pluck a signal like that out of the roaring static of deep space? The answer sits right here on Earth. NASA relies on the Deep Space Network, or DSN, 3 facilities built around massive 70-meter radio antennas located in the deserts of California, Spain, and Australia. They're positioned so that as Earth rotates, at least one dish is always pointed toward the distant probes. These antennas scoop up incoming radio waves across their huge surface area and focus them down to a single point. The catch is that a dish that big picks up everything: radiation from distant galaxies, background noise from Earth's own airwaves, and its own internal electronic noise. So how do you isolate one single ultra-faint signal out of all that? NASA engineers rely on a 3-stage filtering process. First, they eliminate terrestrial radio interference, signals from cell towers, radar systems, and satellites. That's precisely why DSN stations sit in remote deserts, far from civilization, and operate on strictly protected radio frequencies. Second, they need to filter out radiation coming from other stars and galaxies. To do that, the 70-meter antenna is made highly directional, focusing on a tiny, mathematically calculated patch of sky and ignoring everything outside it. On top of that, engineers know the exact baseline frequency Voyager broadcasts on. But because the spacecraft is moving so fast, the frequency is constantly shifted. This is the Doppler effect at work. Think of an ambulance siren. As the vehicle approaches, the pitch sounds high, and as it pulls away, the pitch drops. That happens because a moving source compresses or stretches the waves it emits. Since the probes are speeding away from Earth, their radio waves get stretched out, and the signal's frequency drifts lower. NASA's computers calculate this shift in real time and tune Earth-based receivers to match it, filtering out the rest of the cosmic noise. But there's a third, more insidious problem. Even the receiving hardware's own heat generates noise. The random jostling of electrons inside the metal produces background static that, left unchecked, would instantly swamp Voyager's already faint signal. To get around this, the most sensitive components of the receivers are cooled to near absolute zero. That suppresses the electronic's own internal thermal noise and lets engineers pick out a signal weaker than almost everything else around it. Absolute zero, incidentally, is minus 273 degrees Celsius, the ultimate cold limit in nature, where thermal motion is reduced to an absolute minimum. Only by combining geographic isolation, pinpoint antenna targeting, and extreme cryogenic cooling is humanity able to catch this infinitesimally weak signal from the edge of the solar system. And it's precisely these painstakingly decoded signals that helped explain the anomaly mentioned at the start. Why space began to thicken as the probes left the solar system. Scientists had assumed the exit into interstellar space would be a smooth transition into an increasingly empty environment. But the boundary of our solar system, the so-called heliopause, works differently. Our sun constantly streams out charged particles, the solar wind, blowing outward in every direction and creating a massive protective bubble around the planets called the heliosphere. But the space between the stars isn't empty either. It's filled with cold plasma, gas, and dust left over from ancient supernova explosions. When the solar wind reaches the outer edge of the heliosphere, it runs into and interacts with this interstellar medium. It's a chaotic border zone. the solar wind pushing outward from inside, interstellar plasma pushing back from outside. And right at that boundary, particle density shifts sharply. Today, in 2026, both probes have long since crossed that barrier and are cruising through the cold expanse between the stars. But their time is running out. Their real enemy right now isn't micrometeorites or radiation, it's a lack of power. Out where the Voyagers are, the sun still shows up as a bright star, but its light is far too weak for solar power to be usable. Instead, the Voyagers run on RTGs, radioisotope thermoelectric generators. Contrary to popular belief, these aren't miniature nuclear reactors. There's no controlled chain reaction, no complex electronics, no moving parts to break down over half a century. The design is brilliantly simple. Inside sits a durable capsule containing plutonium-238. This isotope decays naturally and continuously, releasing a steady flow of heat that keeps the capsule extremely hot. Wrapped tightly around it are thermocouples, plates of semiconductor material. When one side of a plate touches the hot plutonium capsule and the other faces the freezing vacuum of space, that extreme temperature difference generates an electric current. But you can't cheat physics. Plutonium-238 has a half-life of about 88 years, meaning it steadily decays and releases less and less heat over time, while the thermocouples themselves also degrade. As a result, the generators lose power year after year. Of the 11 original scientific instruments carried on each spacecraft, only a handful are still functioning today. Voyager 1 is down to 2, Voyager 2 has 3. To stretch out the probe's lives, NASA engineers remotely power down systems one at a time, constantly making tough calls about which instrument gets sacrificed next. Which raises an obvious question: how does the spacecraft even receive these commands? It works through the same deep space network, just running in the opposite direction. While the probe whispers back to Earth at 20 watts, the 70-meter dishes on Earth send out a powerful, tightly focused beam carrying tens of thousands of watts. As that signal crosses the same 24 billion kilometers, it too weakens drastically. But each Voyager carries its own 3.7-meter dish, locked onto Earth with pinpoint precision, acting like a collecting bowl that gathers up those faint scraps of energy. The connection speed is abysmal, a mere 16 bits per second. So uploading a single command package takes hours, and confirming it actually executed takes nearly 2 days. It was through exactly this painstaking process that engineers were forced to shut off even the heaters protecting the instruments from freezing. To scientists' amazement, the vintage electronics have kept working even in the bitter cold of deep space. Even so, the power reserves keep dropping relentlessly. Within the next few years, roughly by the early 2030s, there won't be enough power left to keep even the transmitters running. Engineers will be forced to send one final command, and the connection will be lost for good. On Earth, there will be total silence. But for the Voyagers themselves, losing communication will only be the beginning of their endless journey. Once the transmitters finally go dark, the Voyagers will stop being scientific instruments. But they won't become ordinary space junk. Bolted to the side of each spacecraft is a small package. The iconic golden record, a gold-plated copper disc carrying the sounds of Earth, music, photographs, and greetings in dozens of languages. Engraved on its cover is a map pinpointing our planet's location. It's a message in a bottle, cast into the endless cosmic ocean, meant for whoever we will never meet. Once the signal is gone, their true, silent voyage through time will really begin. In about 300 years, the probes will reach the inner edge of the Oort cloud, the enormous shell of icy bodies surrounding our solar system. It will take them roughly 30,000 years to drift all the way through it, and finally leave the outermost fringes of the solar system behind. In about 40,000 years, they'll make their first close passes near other stars. By then, micrometeorites will have pitted their hulls. Their antennas will be warped, and their metal darkened by radiation, but the sturdy aluminum casing will have kept the golden records in pristine condition. In roughly 5 billion years, the sun will begin to die, swelling into a red giant, and Earth will either be swallowed whole or scorched into a lifeless cinder. But the Voyagers will be long gone by then. Around that same era, another cataclysm may be unfolding, the collision between the Milky Way and Andromeda galaxies. If those galaxies truly collide, the orbits of billions of stars will be radically reshuffled by gravity, and predicting where the two tiny Voyagers end up in that chaos becomes nearly impossible. Maybe they'll drift on the outskirts of a newly merged galaxy. Maybe they'll get flung even further out into the frigid emptiness of intergalactic space. In 10 trillion years, the last and longest-lived stars in the universe, red dwarfs, will finally burn out. Space will fall into eternal darkness, marking the start of the hypothetical era of matter decay. At that point, the very atoms making up the spacecraft's hulls and the golden records will begin to slowly break down. The laws of physics will quite literally begin erasing the Voyagers from existence, but until their very last atom decays, these two small, battered pieces of 1970s metal will keep sailing silently through the void, all remaining among the most enduring things humanity has ever made, and the final proof that somewhere in the universe, on a pale blue dot, there was once life that looked up and dared to reach for the stars.